Okay, so let's jump through these next examples here and see if we can make sense of them. So here in example 5, we need to find the exact, no, we don't. We need to expand. Okay, we need to expand the following logarithmic expression. So here we have ln, as a reminder. Ln of some number is really just log base e of some number, and e is around 2.7 something, you know. There's other numbers there. I think it's 2.7, 2.718, blah blah blah. There's a whole bunch of numbers. It's an irrational number, and the numbers are might as well be random. They go on forever, just like pi. Okay, so we have ln of 2ab over c squared. We need to expand it. So one thing we can do to expand this is apply the quotient rule. So we have ln of 2ab minus ln of c squared. So here what I've done is I've represented this quotient in the input of this logarithm, and I've written the denominator here, and I've written the sorry, that was the, I've written the numerator here, and I've written the denominator here. So remember, you can represent a quotient, a logarithm of a quotient as a difference of those logarithms. So now we can apply another rule to expand this even further. We're going to apply the product rule. So here we have ln of 2 times a times b. I can represent that as ln of 2 plus ln of a plus ln of b. And then I am subtracting ln of c squared. Now, in this last example, and sorry, in this last line, I can do one more thing. I can apply the power rule. So the power rule has the same initials as the product rule, so I will call this the POR. So power rule rather than product rule. Let's call this PR for product, and then PO for power. And so this will just be ln of 2 plus ln of a plus ln of b minus 2 ln of c. So that's not so bad. That's as much as we can expand this. There are no more products to expand, no more quotients to expand, no more powers to deal with. So there you go. That's it. Not so bad to expand logarithms. Here in example 6, we're going to do the opposite. We're going to condense rather than expanding. So let's condense these. So here, first I'm going to apply the power rule. But the power rule in reverse. So I'm going to take the coefficient in front of this logarithm, and I'm going to move it onto the exponent of the input of the logarithm. So this will be log of a to the power 7. Going to do the same thing here. This will be log of b to the power 5. And here, what I'm going to do is actually, I'm going to factor out this negative in front of both of these logarithms. So minus, and then that's going to be 3 log ab plus now 2 log of a plus b. And the reason that, and let's use different inside and outside brackets, just might be clearer reading. Now, the reason I'm doing this is because if I don't factor out this negative, I often make mistakes as to when I should be using the quotient rule and when I should be using the product rule. So I like to only have one negative if possible by factoring out multiple negatives. Now let's apply the power rule again, but I will apply the power rule on the inside of the brackets on the right here. So minus, I'm going to take this 3, and I will write it as the exponent on this entire input, not just on the A, not just on the B, but on both. And then I am going to take this coefficient of 2, and I'll do the same thing. I'm going to apply it to the entire input. So this will look like minus log of AB all cubed plus log of A plus B all squared. And again, I'll do square brackets for my outside brackets, and can't remember what you call these curvy brackets. Curvy brackets for the inside brackets. Okay, so now that we've done that, let's apply the product rule. So let's apply the product rule. Again, our goal is to condense. So we want to bring these logarithms together into one logarithm if we can. We will be able to in this case. So the logarithm of a to the 7 plus the logarithm of b to the 5 is really just going to be the logarithm of the product of those two inputs, a7 times b to the 5, minus, and let's collect these two inputs as well, right? So this is the sum of two logarithms of distinct inputs. So we take the product of those two inputs. So this is going to be AB all cubed times A plus B all squared. So that is the new input. So all of what we have here in these square brackets, these two logarithmic expressions, have now been condensed into one logarithmic expression right here. And let's make some room. And we are going to, we have a difference of logarithms here, so let's apply the quotient rule. So the quotient rule says that we just can write these two logarithms in this last expression as one logarithm. Let's do big square brackets because we're going to have a big quotient. So we're going to have this first logarithm as our numerator. I'll color code these inputs. So this first logarithm is our numerator. And this second logarithm, the input of that second logarithm is going to be the denominator. So let's do that in blue. So we're going to have AB all cubed, which I can just write as A cubed B cubed. Right, I'm just taking this and I am distributing this exponent into each of the factors inside the brackets, times A plus B right here, all squared. And all I have to do at this point is simplify. So here, this is really just the logarithm of, well, a to the 7 on top, a to the 3 on the bottom. Everything is being multiplied in the numerator. Everything is being multiplied in the denominator, so I can cancel out these factors. This will be a to the 4. This will be, let's maybe do square brackets. A to the 4 on our numerator. And then b to the what? Well, b to the 3 on the bottom, b to the 5 on top. That will now be an exponent of 2. Because we take the difference of those exponents, right? B to the 5 minus 3 is 2. All over a plus b squared. A plus b squared. And we can't simplify this anymore. This is actually as simple as we can get. This denominator, if we expand it, we'll just get a squared plus 2ab plus b squared. And we'll have just a series of terms on the bottom, and we can't cancel out individual terms with factors on the top. So this is as simple as we can get. And it does, although this looks complicated, it is definitely simpler looking than this. So that's what it looks like to condense a pretty beefy looking initial logarithmic statement, logarithmic expression. Now, let's keep this in the same video. Let's just simplify. Let's do example 7. We're going to simplify example 7 here. So for example 7, I have 1 over log base 2 of 6 plus 1 over log base 3 of 6. And eventually, what you'll be able to see here is this is a clear case where we can apply this log rule. But we're going to apply it in reverse. So we have 1 over some logarithm, and we can just write that as the logarithm where we switch the input and the base, right? So this is log b of a, and if we have 1 over log b of a, that's just equal to log a of b. So let's apply that rule. I'm just going to write that rule on the side here. So log, just so that we can keep track of the rule as we apply it. So log a of b is really just 1 over log b of a. So we can say that 1 over log 2 of 6 is really just log base 6 of 2. Right? I took the reciprocal, which is allowed so long as I swap the input and the base. The old input was 6, that's now my base. The old base was 2, that's now my input. So I can take that reciprocal and it still represents the same value. Same thing here, right? 1 over log base 3 of 6, swap the base and the input. So this is going to be log base 6 of 3 now. This is a big advantage to do this because now we actually have logarithms of the same base, and so we can apply the product rule. So the product rule is really just noticing that we have a sum of logarithms, and we can just write that as one logarithm where we take the product of their inputs. 2 times 3 is 6. So there we go. Applying the product rule, we now have log base 6 of 6, which is really just 1, right? 6 to the power 1 equals 6. So there we go. We've simplified this as much as we can. We've simplified this so much that we've actually evaluated it. We found a simple number value for it. So so this rule, it can be tricky to notice that that this would be a place to apply it. One other hint that this is a place to apply this particular rule is to notice that we have 1 over some logarithm, 1 over some logarithm. We're taking the sum, and their inputs are identical even though their bases are different. And if we apply this rule, then because we're swapping the inputs and the bases, then when we do apply that rule, we can see that we'll now have logarithms of the same base. And if we have logarithms of the same base, then we can apply certain properties of logarithms like the product rule, and we can collect them together more simply. So it does take a while for this to feel natural. I will at some point do this bonus example for you. This bonus example is not a problem I can take credit for. This is actually a problem that was put forth by YouTuber 3 blue, 1 brown. It's a fun problem to do, and it actually applies the rule that we just did. So I will eventually see you in that video as we do this bonus example. I'll just keep in mind, though, that this bonus example is not something that I would show you on a test or anything, but it is fun. It is fun to explore.